This screencast is on electronegativity. Please have your periodic table of elements available, as well as your periodic chart of ions. We'll review by first taking a look at orbitals, and that's known as the Pauli exclusion principle. And it says that an orbital can hold a maximum of 2 electrons. And we refer to those electrons as a spin and a counterspin. And we looked at this a little bit further by taking our periodic table of elements, dividing them into the block orbitals, the s, p, d, and f, actually putting spins on those. And this chart or table is actually available in Sakai for you. And it's just a little learning diagram to show you how the orbitals are first loaded with electrons. And if we go a little bit further, we see actually the orbitals look more similar to this, where this is the s orbital, and there's a maximum of 2 electrons in it, and they spin around in a globe. So this is a 360-degree globe, three-dimensionally. When we get into the p orbital, they'll hold a maximum of 1, 2, 3 types of orbitals with 2 electrons each, so that's 6 orbitals, and they spin like this, three-dimensionally. The d orbitals get a little bit more complex, and they start looking like this, so there's a maximum of the 5 here, times 2, which is 10, and then we have 14 for the f orbitals. So as we look at these orbitals, they get increasingly more complex. And remember, it's the electrons and how they interact with the atoms or the protons of the nucleus with atoms of elements is what determines their bonding. So let's look at the easiest example, hydrogen. We know that it's simply a nucleus with a proton and an electron. When it bonds to itself, it shares 2 electrons in a covalent bond. And we represent this with a stick diagram or ball and stick diagram. You see the 2 hydrogen elements spinning around on the end of the stick, and there's really no such thing in nature. This little stick here doesn't really exist. There's really just the atoms with the spinning electrons around in spheres that are attracted or share electrons, and they form this covalent bond between 2 non-metals. Let's take a look at electronegativity next. This is a table, and it shows the electronegativity values based on the Pauling scale. And this is slightly different than the text uses, but it's all very similar and is all valid. We can see from this, based on these numbers, that all the high numbers are up here in the upper right, and they are centered around fluorine, with a value of 4 is what it's normally referred to. That's the maximum scale of the electronegativity. And then some of these noble gases here are not measured values. And down here, as is typical, we have the lower corner of the values, which is francium, similar to other periodic table trends. And if we were to take a blank periodic table and draw an arrow, we could visually see how electronegativity increases. So let's do that, and we see that it increases from the bottom left to the upper right. And that's really what you need to know is in the bottom left, these are low values, hovering around 0.7, and it goes all the way as high as 4 for fluorine. Let's look at the electronegativity table again, and we can see or visualize that it makes sense, because if we take our typical examples of ionically bonded compounds, we see that sodium chloride, If you look at the two differences between these numbers, sodium chloride, chloride has a 3.16, sodium has a 0.19, and that tends to be a relatively high electronegativity value. And what does that mean? It means that the electrons that they share are more attracted to the chlorine atom than the sodium atom. And that makes sense because really an ionic bond is considered a transfer of an electron. And those forces kind of hold it together. And when we visualize those molecules or compounds in the book and look at them, you'll see two little round globes representing those atoms, and they're kind of next to each other. Now, if we look at something else, like for example, a diatomic element or molecule, let's take, for example, one of the diatomic elements here. And of course, there's nitrogen all the way through fluorine, chlorine, bromine, iodine, and hydrogen. If it bonds to itself, of course, the electronegativity between the atoms is zero, because if you have two atoms that have the same electronegative values, you subtract them, and then you would expect the bond to be pretty neutral as far as electronegativity is concerned. So that's considered a non-polar covalent bond versus something else like two nonmetals forming like silicon dioxide. That'd be more of a polar compound because electrons are spending more of their time around oxygen than silicon because it has a higher electronegativity value, and that's a polar covalent bond. And we'll show you examples of these right now. Here's our first example. We talked about hydrogen. We know that since they're the same elements, that their electronegativity difference is zero. And if you get somewhere, and this is a scale which is kind of a little bit sliding, it's not absolute. We just know in general that the covalent non-polar compounds have values of electronegativity difference between 0 and 0.4. An example would be the diatomic molecule hydrogen. And then let's go to another very important example, water, which is considered a polar covalently bonded compound. And that just means that the electrons like to spend more time around oxygen than the hydrogen ones. The oxygen electronegativity value is higher than the hydrogen. And then when we start getting a difference somewhere between 1.8 to 3 or somewhere around there, really the electrons move all the way across, and it's no longer considered shared, but it's considered a case where it's given from, or it's transferred from the sodium to the chlorine, and we represent that like this little figure here. So let's look at carbon dioxide again. And we know that carbon dioxide, the Lewis dot diagram looks like this. And what I did is I used the valence shell electron pair repulsion theory, the Vesper theory, to kind of show you that the electrons try to push away from each other so they're balanced. So these electrons are not attracted to each other, so they push each other away. Opposites attract, and then similar and negatives repel each other. So they're repulsed, and you get something that looks like this for the dot diagram. And then we represent the electronegativity difference as a dipole, and that's what this arrow with the little cross is. It goes from the positive, which is a plus delta, that's just a Greek little d for delta, Greek symbol, to a negative little d. So it goes from a positive to a negative. And on this side, it does the same thing. So you can look at it as a linear molecule and has carbon in the middle, oxygen, which is more electronegativity on each end. And that just means when you look at this diagram here on the left, the electrons spend more time as they're zooming all across here, all around, on the oxygen side on either end, then in the middle with the carbon, and you see it's a slight hourglass. And this is just one representation of what the electrons may look like. If we were to look at it another way, we would see that this molecule, the bonds, are actually polar, meaning one part of the bond is more electronegative than the other, and these are the dipoles representing that. Both the bonds and a molecule may be considered polar. In this case, since the two vectors, which are the dipoles, are equal and opposite, the molecule itself is not considered polar, but the bonds are considered polar. Let's look at our third example, and we'll diagram the water molecule to great detail here. We first start with the hydrogen. We know that there's one electron in hydrogen, valence shell, so that's 2 total. And we know in oxygen there's 1, 2, 3, 4, 5, 6 total. So that leaves 8 electrons available to bond, and it forms an octet, and that's what they like to do. And this is how it's drawn, kind of real pretty, common way to represent a Lewis dot diagram. And we could also look at this Lewis dot diagram as almost a tetrahedral type shape, where if you look at this in 3D, all legs of the tetrahedral are equally balanced. So on 4 sides there are electrons, and on 2 sides there happens to be hydrogen atoms connected to them. As we look at the dipoles, we can see they go from hydrogen to oxygen, hydrogen to oxygen. They both are forming a vector which results in a polar molecule, which is shown here when you look at the rotating molecule as this gold arrow here, and that's the polar orientation and which direction is polar for that molecule, versus the dipoles, which is the polar bonds of the molecule. So take a look at that, and we see that the oxygen is represented by a negative delta, which means the oxygen is more electronegative than both the hydrogens. And this is the resulting view of it. If you understand each of the components of this rotating hydrogen molecule, it'll help you understand how it bonds with other water molecules and why the bonds are how they are. Because as you look at the stick diagram, it doesn't really show those 2 electrons on the other side of the oxygen molecule. There's actually 4 electrons or pairs surrounding it, and according to Vesper's theory, valence shell electron pair repulsion theory, these all repel each other and form a tetrahedral type shape, and this just happens to be one version of that. And we'll get into molecular shapes in another screencast. And here it is one more time, just concentrating on these 2 elements, the dipoles, which are opposite pointed vectors, and if you combine these vectors, they point in the middle towards kind of the middle direction, and they reinforce each other versus cancel each other out. And this is a polar molecule, and it's more electronegative in the oxygen side. Thank you for watching this screencast.